is the memory predicate that is satisfied only by the empty heaplet, the one whose domain is the empty set. Okay, so this definition, any user can write down one of these data structure definitions, right? This is not built into verifiable C. This data at is built into verifiable C and emp and star, but then you make your own data structure definitions using just the programmability of the Coq logic. All right, so back to the program. Let's run it. So let's start here. P points to the beginning of some linked list. Let's set W to null. There we go. W is grounded. V gets P. Now, while V is not null, right? V is a true value at the moment. So let's do T gets V arrow tail, and V arrow tail gets W. So there we are. There's that picture. And then let's set W to V and V to T. And that's that picture after one iteration. And if we run this, well, V is still not null, so let's run it another iteration. And another. So you can see it's sort of reversing the list in place. And we'll do one more. And now V is null, so the loop terminates. And we return W, which is a pointer to a linked list representing the reverse of the original list. Well, that's a proof I just gave you. We don't need Coq anymore. But now let's reason about this proof in verifiable C. So we'll write a function specification for this reverse function. Here is the function prototype written in C as you'd see it in the header file. And its function specification in separation logic says, well, there's a precondition for calling this function. And here the precondition has a free variable P, right? That's the function parameter. Then we'll run reverse and assign its result to some return value. And there afterwards, the return value will be a linked list representing the rev of sigma. Okay, so in this program, there's a while loop. And in Hoare logic or in separation logic, the proof rule for the while loop looks the same. That if I is a loop invariant, and whenever I is true and the loop test evaluates to true, you can run C, the loop body, and if it finishes, it will terminate in a state satisfying the loop invariant. And then also if, whenever the loop invariant is true and the negation of the loop test, that implies Q, then the while loop is correct with respect to the precondition P and the postcondition Q. Okay, so that's the while rule. And so to apply the while rule to this program, we need a loop invariant. So there's a picture of the loop invariant. At any point here, when we're at a place where the loop invariant ought to hold, W is a linked list representing the reverse of something, or I guess representing sigma 1. V is the head of a linked list representing sigma 2. And the original sequence is the reverse of sigma 1 concatenated with sigma 2. And so there's two existentials here. Exists sigma 1, exists sigma 2. And it's very typical that there's an existential at the head of a loop invariant. Okay, now, here we have to resort to using the mathematics of the application domain. Here our application domain is sort of abstract mathematical sequences, which in Coq we call lists. And there's a rev function in the Coq library that we're relying on, right? The Coq library has in it enough of the mathematics of our application domain. If it didn't, we could of course implement lists and implement the reverse function and prove things about it. Just as you did, I don't know, in the Coq intensive last week. Okay, so, summary. In Coq, well, when we write assertions in separation logic, it's convenient to divide them into three parts. So this assertion describes something about the state of our C program at some instant. Prop contains the pure propositions. Local contains information about the current contents of our local variables of the C program. And sep is the separating conjuncts, the things that describe space, what's in memory. Okay, so here we wrote exist sigma 1, exist sigma 2, and we talked about W and V. Well, this was an all too clever idea that Tony Hoare had in 1971. Let's confuse the variables of our programming language with the variables of our logic so that we don't have to treat them as two different kinds of things. But they are two different kinds of things. One has different values at different times. That's the program variables. And the other, you can quantify over and destruct on. That's the logic variables. And when we're doing real proofs as opposed to whatever they do with pencil and paper, it's really helpful to distinguish those. So here we'll say underscore W is the C language program variable. And at this time, that temporary contains the Coq value W. And underscore V is a C program variable, and it contains the value V. And here we'll quantify over the values W and V. These are existential quantifiers. Val is the C language value type, the things that can be in C variables while you're running. And the different kinds of value types are, integers, floats, pointers. Okay. And then we'll quantify over sigma 1 and sigma 2 here, just as we did in the sort of pencil and paper version. And here, this squiggle we'll write as list rep, the representation of a list. W is the address that represents the list S1, and V is the address of a data structure that represents S2. So that's our loop invariant written down in verifiable C, right? And this prop local sep is just a notation in Coq. And then our function specification, this is the specification of the reverse function. Underscore reverse is the name of the C language function. This with quantifies some variables that we can use in both the pre and the post condition. So sigma, this sigma, notice it appears here and it appears here. If you're going to use a variable in logic, you ought to quantify it somewhere. So that's what this with clause does. There's a precondition and a postcondition. The precondition has access to this C language variable, underscore P, which is the function parameter. And here's its C language type, pointer to struct list. And then the precondition is this assertion. No new propositions are true. The parameter underscore P contains the value P that was quantified right here. And in memory, at address P, there's a list representing the sequence sigma. And the postcondition returns some value, the ret temp of type pointer to struct list. And the postcondition is this. There exists a value Q such that that value is in the returned temporary, the ret temp. And in space, in memory, there's the separating conjunct. Q is the address of a linked list representing the reverse of sigma. So there's our function specification. And now, let's prove it. Okay, but let's not prove it here. Let's prove it in Coq. So there's our program. Let's see what we got in this program. We got our struct definition. We have an extern initialized global variable with enjoyable address arithmetic that makes a little linked list of length 3. This is the C language. If C does crazy things, then we have to have a program logic to reason about the crazy things. Here's a little function that adds up the elements of the elements of a linked list. But here's our reverse function, exactly as I showed it to you on the slide. And here's a main function that, what is this? Okay, and here's a main function that calls it. So we will use the parser of the CompCert-C compiler to parse this program into an abstract syntax tree represented as an inductive data type in Coq. And we could even look at the abstract syntax tree. Here's the output of the CompCert front end, the parser and sort of the first compiler pass. And it produces this file that we can, and here is, I don't know, the body of the reverse function. It's got its type, its function parameters and their types, and this sequence of commands. This is not very interesting to look at, but it's just a data structure. And our proof in separation logic will be just, that will be the function body that we stick into the proof of our data structure. Okay, so let's do this. In this verif reverse.v, I should mention, this is from Software Foundations, Volume 5 Beta. Well, it says Volume 5 Beta, but it's really Volume 5 Alpha. Sorry about that. And it's how to do proofs in verifiable C. And Chapter 1, which I'm going to skip in this lecture and maybe come back to in the next lecture, is just an introduction, and this verifies a program that adds up the elements of an array. This chapter, verif reverse, is the one that I'm going to work through right now. And this chapter, verif stack, is your homework. So I have a little program that does implements an abstract data type for stacks using linked lists, and I'll introduce the homework at the end of this lecture. And then, if you don't want to do any other lecturer's homework this week, you could try out verifying this implementation of a hash table with external chaining. And maybe I'll talk about that in a lecture or two. Okay, so let's do a proof. Step 1, we import the VST Floyd proof automation system and program logic. So that line always looks the same in your VST verifications. Second, let's import the parsed abstract syntax tree of the program we're going to verify. That was in reverse.v, so we'll import reverse. And the next two lines always look exactly the same. Let's let Coq compute some things about the struct definitions and the global variables of that function. Now, tstruct. This is from CompCert-C. It's the CompCert-C type syntax, right? The abstract syntax of types. There are int types of various sizes and signedness and attributes, like how they're aligned in memory, and the long type, and floats, and pointers, and arrays. All right, this is the deeply embedded description of C language types. And tstruct is one of those constructors. Underscore list, it's a positive number. It's 2. Okay, the CompCert compiler picks arbitrarily numbers to represent identifiers in its symbol tables, and this list type that we defined in the source program in this particular verification really stands for 2, although we don't need to know that anymore. It's just, list is just a number. It's not a Coq variable is the main point. And let's define this convenience definition. T underscore list is this struct type. Okay, now, preliminary to specifying and verifying this program, we need to define what is a linked list using that struct type. And so this definition here is exactly what I showed you in the slides before. It's this fixed point over sigma. Okay, what's next? It's convenient for the user-defined separation logic predicates. Let's not let the simplifier simplify them automatically. When we want to unfold them, we'll unfold them explicitly. All right. I'm going to skip these and move on to what am I skipping? When you define a user-defined predicate, it is a good idea to define a couple of standard lemmas about that predicate that you can put into the proof automation hint database about that predicate. So for example, if P is a list rep, then it is a valid pointer that you can test for null. But I will spare you the details for now. And let's talk about the specification of the reverse function. Well, this is exactly what I showed you on the slides. It's the claim that right, that you could make about the reverse function, that it satisfies this precondition and that postcondition. Okay, now, in general, our program is going to have several functions, and they could call each other, even recursively or mutually recursively. And when you verify one function body, and you get to a function call of one of the other functions, you'd like to make use of its specification. So we want to collect together all the function specifications into a global context, and then we can use that global context in the verification of each function. And when a function is recursive, we'll collect it, it can make use of its own specification from the global context. And is that circular reasoning? No. Okay, so, well, I proved the logic sound, so it must not be circular, or Coq is unsound or something. Okay, so this program has only one function of interest, so we'll collect it into this gprog, which is a list of fun specs. And this, with library tactic, adds in the specifications of all the built-in functions that CompCert adds, which are not interesting here. Okay, so
using tactics in terms here.
Well, yes, I'm using a tactic and a term. This is 2018. It's not 2005 anymore. So yeah, it's very convenient. Okay, now here is the proof that the function body satisfies its specification. Here's how to read the statement body reverse. SemX body is a predicate that says a function body. Now what is f reverse? It is this. It is exactly the abstract syntax of the program as parsed by CompCert. So it is the function implementation. And it claims f reverse satisfies reverse spec. What is reverse spec? It is exactly this thing that I defined here. It's the claim about the precondition and the postcondition of the function. And this is in the context vprog and gprog. Vprog is information about the types of global variables, and gprog is information about the specifications of global functions. It's that thing that I defined right here. Okay, so that's the statement of the lemma. Now let's prove the lemma. There's our proof obligation right here, SemX body. And the way you prove a SemX body is you prove that the function body satisfies a Hoare triple with that precondition and postcondition. And this tactic of VST Floyd, start function, gives you that proof obligation. So there we are. And here we've sort of abbreviated away the postcondition and the more commands, but in fact, there it is. Let's see what happens if we unfold the abbreviations. We get this. Here's the function body. Here's the function body. It looks like, almost like C syntax, but that's just a printing only notation in Coq. How wonderful is Coq that it can do that. All right. How wonderful is Jason Gross that he showed me how to do that. Okay, now, here is the precondition. This comes directly from the fun spec that I showed you before. And here's the postcondition. And this comes directly from the postcondition. And what else? This part of the postcondition was not in the fun spec. It says, when you get to the end of the function and you're about to return, you have to give back your addressable local variables. That's memory. You have to give back your stack frame. This function doesn't have any addressable